So what delayed you earlier with the speaking exam? Because by the time we finished, our class was practically over. Did you start late or?
Well, we did start late, yes.
How's that again? You started a little late?
Started a bit late, and
Yeah.
then because it's 3 people,
It went up extra. I thought it might, yeah. So you're talking for 20 minutes?
Oh, in total.
Mm. It's kind of funny, you have to introduce yourself, but the three of you know each other for the last 10 weeks. So you have to say, hello, I'm Lynn. I am from China.
They asked ourselves, they asked each of us a question before.
What did you get?
What do you do to relax?
And your answer?
Play Sims.
Sims. You play Sims?
But only beauty, basically.
Okay. And Lynn, your answer?
How to spend your free time.
And you said?
I don't know. I would say something like workouts, doing sports.
Ah.
Something like that.
And Gina, what did you get?
I think it's introduce a place and a food in your country.
Ah, what food did you pick?
Noodles.
Ah, classic Chinese dish. That's like if I said potatoes or something, isn't it? Right. Can you read the start of the question? So what's this one about? Lynn, you go ahead and read it to us.
What is latent heat of fusion?
Good. Okay. Now, without looking at the answer, what would you say? This is A part 1, is it?
Yes.
Yeah. What would you say latent heat of fusion is? The energy required to do what?
To change
Yeah.
1 kilogram of substance.
1 kilogram.
Change the state of 1
Yeah.
kilogram of substance.
Okay, now if I've written 1 kilogram, so I'll have to say now the energy required to change 1 kilogram of, and because it's fusion, it's a solid to liquid, isn't it? Yeah, so we'll say the energy required to change 1 kilogram of a solid to a liquid. Very good. Without changing the temperature. Very important you say that. How many marks was that one now? 2?
2.
And do you know why it's 2, of course? Because it's going to be 1 mark for this, and then 1 mark for this, I'm going to imagine. Okie dokie. Next, Lynn, part 2.
An ice cube of mass 0.105.
Hang on, let me just draw that. 0.105 kilograms?
Yeah. Is removed from a freezer at a temperature of -18 degrees.
Okay.
And is placed into a well-glass cooper.
Yeah.
Can of glass.
Yeah.
0.206 kilogram.
Okay.
Containing 0.18 kilogram of water at a temperature of mixture has reached an equilibrium temperature of 5 degree. If it is assumed that no.
Oh, hang on a second, sorry. What's at 5 degree? The water?
The mixture stripped ice has all melted and.
No, you need to go back a little bit. I'm back at the 0.18 kilograms of water. Is it water that's in the copper?
Yes.
Yeah.
So what temperature is the water at?
Temperature.
55 degrees Celsius.
The water's at 55. Okay. Now, do you know I would imagine then also that the copper is at 55 as well, if they're in equilibrium. So yeah, you said, Lynn, that you put this ice. Sorry, continue. What happens? What do? You put the ice in the water or something, is it?
Yeah, until the ice has all melted and the assumed. Oh, and the mixture had reached an equilibrium temperature at 5 degrees.
Okay, so you put the ice in and it reaches 5 Celsius.
Yeah.
Yeah. So what do they want?
It would assume that no heat is lost or gained
Yeah.
in the system, determining the specific lasting heat of
Yeah.
fusion of house.
Okay, and they must give you the heat capacity of ice.
Yeah, ice, water, and cooper.
Yeah, of the triodome. Great. Okay, so let's think about this logically. What is gaining energy?
Guys,
The ice. And what is losing energy? The water and the copper. So, what happens to the ice? Two things happens. Firstly, C. What's the C for ice? 2181 or something?
2,100 joule kilo.
Two's te- two
100
Yeah, 210.
2100.
joules.
Ah, yeah, don't worry about the unit. Yeah, 2100. So it has to go from minus 18 to 0, right? And then what happens next? Well, then it melts. So that's latent heat. So that what formula is that? That's mL. Then what happens after it melts? Then it has to warm up to 5. Is it 4181 they use in this question for the
Yeah, 4180.
41805? That is the heat gained by the ice cube. Okay? That has to equal the heat lost by the water plus the heat lost by the copper. What's the heat capacity of the copper, please?
385.
And it also drops by 50. Yeah? This is the gain. And that has to equal what is lost.
What is that again? 0 from 105 times 2,100 times.
Oh, that's the ice warming from minus. Oh, sorry, what the heck? Sorry, that should be an 18 there. It looks like a 0. How the heck did that happen? That's a 18. Yeah. Okay, is that okay? Yeah, so if you rearrange this in your head, you'll get L equals 0.18 times 4180 times 50 plus 0.206 times 385 times 50 minus 0.105 times 4180 times 5, whoops, ran out of space, minus 0.105 times 2100 times 18 all over 0.105. That's 4180. Okay, so let's type this in on our calculators and see what the heck we get. Should be a pretty big number. 3138 times.
10 to the power of 5.
Yeah, yeah. And the unit is joules per kilogram. So that seems right. 3138.00000 joules per kilogram. Let's put this 1, 2, 3, 4, 5, 6. So that would be 3 significant figures. 314. Is that right? Let's see, hang on. 1, 2, 3, 4, 5, 6.
Oh, it's 3.38.
Oh, sorry, I misheard you. What did you say your answer was?
3.38
3.38
times 10 to the power of
5 joules per
5
kilogram. Yeah. Or that's 3, I think, hang on. 3, 1, 2, no. Is that 338 kilojoules per kilogram? Why am I messing about with the units? Which you can also write as 338 joules per gram if you want to cancel the kilos, but let's not be stupid. Okay. How many marks was going for that one? What do you think about that?
There's specific letters of the process that we see.
Yeah.
For every process that you get right.
There's marks for basically each one of these in the numerator. Yeah.
How much max will I lose if we write the wrong units?
The wrong units? 1.
What if the process is right by the 1 digit is wrong, and then you get like.
Then you lose the last mark, the answer mark, I think. Yeah. I think so. That's usually how it works. Right, what's next, Lynn? Is this A3 or B?
It's A2.
A2?
Yeah.
Oh, we just did A2.
Oh, the next one is
Yeah.
B1.
B1. Okay, go ahead.
Describe an experiment that demonstrates Brownian motion.
Ah, good old Brownian motion.
Yeah.
Gina, want to tell me an experiment for Brownian motion? Oh, don't worry. You can practice your speaking. Tell me how to do an experiment with Brownian motion. First, tell me what do I need? Yeah? No, don't check your notes. Just tell me in whatever English you have, what do we need? Now, if you don't know, that's okay. Oh, no, don't check your notes. Don't. I just want to see if you can describe in your words what to do. Okay. I think you're a little shy, but that's okay. Dorian, do you want to try?
We need a box.
Good. Step 1. We need a box. That's all I wanted, Gina. That's all I wanted. So, what do I need to put in the box, Gina? Put molecules in the box. Let me just take out my molecules. 1, 2, 3. What else? No, you're right. You have the right idea, though. I'm only joking. You do need molecules in the box, but how do we get the molecules in there? Like, what do we do to put it in? Very good, Gina. Thank you. So, you know what I'll do? I'll probably make my box. Maybe I'll make it look like this. I'll put it like this, and then I'll have the smoke rising up through it like this, something like that. Okay, so I'll just put a little hole here. I suppose I don't really have to. So this is a smoke source. I don't know, I guess it could just be a candle, i.e. a candle. Okay, so this is our box. I suppose we better let the smoke. No, I think we should have it closed, perhaps. What else do we need? We need some way to look into the box, don't we? So there's my eye. Come on. The heck? Come on. What's going on here? Got it stuck. Anyway, okay. Okay. The viewer. Okay, and then we'll probably need to put in here some light source as well, huh? Okay. So in what way does this experiment work? You observe via the viewer, which is actually usually quite like a microscope. The motion of smoke particles in a lit closed box. The smoke will appear to, what way will it move? Idly? No.
Random?
Yeah, but we had a special word. It is random, but
Something to walk.
yeah. Put the two words together. There you go. The smoke will appear to move following a random walk, i.e. Brownian motion. Okay. It's okay. I ate too much for lunch. I'm stuffed. Do you all have lunch? What you have?
Arancini balls.
Huh?
In the canteen today.
What are they called?
Arancini balls.
The heck are those?
Apparently it's like this Italian dish where you kind of roll rice, cheese and potato onto a ball
Oh.
and fry it.
And it come in a sauce or something?
Yes.
Yes. Was it good?
I don't like cheese, but it's good.
You don't like cheese?
I don't know, it is that kind of cheese.
Oh, okay. Have you ever tried blue cheese?
Yes.
It's great.
Oh.
I have it every Christmas. Blue cheese. It is strong.
I tried. I can't.
Ah, it's wonderful stuff. Blue cheese with ginger and red wine. Yeah, serious business. Have you tried blue cheese?
No.
Have you tried blue cheese?
No.
Do you know what I'm talking about, blue cheese?
Yes.
It's very smelly, very, very smelly and very, very strong. I guess it's like our version of kimchi or something. Isn't kimchi very...
Kimchi is not as
No.
smell.
No, it's not smelly. I thought it was smelly and strong.
You should try the stinky tofu.
Stinky tofu. Yeah, it's like stinky tofu. Okay, do you all have that written down now? Yeah? What's the next part, Lynn? B2, is it?
Yeah.
Oh, let me guess. Is it going to be... Oh, no, maybe not, actually. I was going to say... what evidence does this provide for the atomic model or something? Is it B2? No? What is it? What's it say?
State for basic assumption of next zero.
I knew it's something related to the atomic natures. How many assumptions?
4.
Flip 4. They usually only ask for 3. Okay, let's see. Right. Assumptions. Number 1, the collisions are elastic. Number 2, there is no interacting force, e.g. charge. Number 3, we have a low density. Number 4, I think we want to talk something about maybe no potential energy.
Something to do with gravity.
Yeah, like no gravity, no potential energy. Okay, Lynn, what were the 4 examples they gave? Let's see.
So the molecular forces are invisible except during a collision.
Right, that's the same as what I said here, number 2. Okay, go on.
The volume of the molecule is invisible compared to the volume occupied by the gas.
Oh, that's a fancy way of saying. No, it's not quite saying low density. Right, go on.
The time occupied by a collision is invisible compared with the time between collisions.
What? Say that one again. The time.
Occupied by a collision is
Yeah.
invisible compared with the time between collisions.
Oh, that's stupid. Yeah, go on. Give us another one.
The molecules move with a uniform velocity between collisions.
Oh, that's also stupid. Right, what else? Is that the 4 he gave?
Yeah.
See, the problem is when you go, I'm sure if you look at different years, you'll get different assumptions. All those things are true, but I wouldn't consider them to be the most important things. Like, for example, his one about the time for collisions, the time interval a collision takes place in is less than the time between collisions. So for example, if it takes 3 seconds for 2 of them to reach each other, the time they spent in contact is less than 3 seconds. Okay, now I get the same thing by saying low density. A low density means that the particles have to travel quite a distance before they collide. So it's kind of the same thing. Also, I said the collisions are elastic. That means there's no energy loss when they collide. Was any of his points similar to that? Dorian, maybe you could read through the 4 of them again. What was the first one?
I have to.
Oh, okay. Gina, do you have the 4 there? What was the first one?
The intermolecular forces are
Okay, so that's definitely fine. Right, what's the next one?
the volume of the molecules is invisible compared to the volume occupied by the gas.
That's kind of the same thing as low density, I guess. All right. Next one.
The time occupied by a collision is invisible compared with the time between collisions.
That's the same as collisions are elastic.
It's not the same as collisions are elastic. No, actually, it kind of is. Yeah, I would have preferred if he said collisions are elastic, which is what it usually is in the exam. But I guess the way he said it kind of means the same thing, because if the time was quite long, then it means, yeah, okay. And the last one?
Molecules move with a uniform velocity between collisions.
Okay, that's the same thing as no potential energy. Because if you think about it, why would the molecules not move with uniform velocity if gravity was accelerating them down to the earth? Okay. Right. Gina, can you read the next question? What is it? C part 1?
It's a complement of.
Sorry, just before you read it, is it C part 1 or B part 3?
No,
C part 1.
C part 1. Okay, go ahead, Gina. Thank you.
Volume 0.130 liter fluid contains 15 moles of ideal gas at a temperature of 25 degree.
Okay.
And the first question is determining the pressure in the container.
Okay, so PV equals nRT, isn't it? So P equals nRT over V. Have you done that formula with Lorraine? Don't forget your 273. Okay, what do we get? Two, three, yeah?
Why is it 15?
Ah! So there's so much food in my stomach, it's reaching my brain. Like this? So that would be 228,000 pascals. Or, in other words, 228 kilopascals. Right-tio. What's the next one? Gina?
Determine the number of moles of gas that need to be released from the container so that the gas left in the container is at STP.
Now, STP means what from chemistry? Standard temperature and pressure, right? Now, do you know what's stupid? Let me tell you what's stupid. STP is not STP. There's nothing standard about it. There's different types of STP. So, for example, in chemistry, what temperature do you use for STP? Maybe, I don't know, you use room temperature, do you? I don't know. Yeah, I don't know. But I think in physics they use 0. What does it say in the question? Yeah, do you know? So there's nothing standard about STP. It's ridiculous. So let's write down our new info. V is 0.13. N, we don't know. T is now 0. And, sorry Gina, what did they want us to achieve? A certain pressure, was it? Or
Number of moles of gas that need to be released.
oh yeah, for STP. And what's the pressure for STP? Is it 10138 or something? 1.05 times 10 to the 5.
So sorry, just now. The question just now,
Yeah.
before the answer,
Yeah?
was it, did you get that? Were you getting
228?
Oh, no, it's 2.8 actually.
2.8.
Yeah, 2.8.
Yeah.
Okay, fine. Right, right, so what formula do we need? Exact same formula, isn't it? PV equals nRT, so N equals PV over RT. So that's 1.01 times 10 to the 5 times 0.13 over 8.31 times 273. As easy as that. Right, what do we get?
$6.01.
6.02. Yep. Times. Oh no, just that's it. Now, we have to be careful because as Gina read, the question said how many moles are released. So the answer is 15 minus 6.02. which is 8.98
Yeah.
moles. Right, how many marks is that one now just done? 3? Okay. And Gina, is there more?
Yeah, that's it.
Last part?
Yeah, that's the last one.
What's next? Oh, no, that was it. Okay.
Why is 15 marks?
Because the question said how many are released,
Wait,
didn't it?
Yeah.
Do you know what they mean when they say how many are released?
Yeah, no, but
Yeah.
with 15 numbers come.
The original. It was originally 15 moles.
Ah, okay.
Right. So, answer me this. For your preparation, what way do you want to be taken this week and next week? Do you want to be doing questions in class? Do you want to be seeing questions in class? Do you want to be mixing them? Do you want to be doing A's? Do you want to be doing B's? Do you want to be doing full exams? Do you want to be doing certain topics? Your personal opinions, please. What do you think would be most helpful to what you want and need?
I think maybe we can start by tackling really difficult topics that you might not understand first.
Do you know which ones those are?
Yeah.
Do you have an idea?
Yes.
Let me guess. Can I pick some?
Mm.
Would it be projectiles?
Mm.
Projectiles
Oh,
are-
about projectiles, yes.
Would it be or would it be turning forces?
No, it's
No, that's okay. Good job. Simple harmonic motion.
okay.
It's okay for you.
Sure.
Not for you.
Yeah.
What topics did you have in mind?
Maybe I see.
I'm still actually not used to the electric one, and that's why.
Yeah. Okay.
The-
Sorry. What did you say, Gina? You had some topics. SHM is a problem. And sorry, what else? We have SHM identified as one problem. What did you have in mind, Dorian?
I do an RC
The IV graphs
and RC.
and the RC stuff.
So you can be confused.
Okay. Yeah. And Lynn?
Pendulum.
Pendulum is good because that goes into simple harmonic motion as well.
And,
For some reason, when it comes to Young's modulus,
Young's modulus.
I don't know.
What the
I
heck?
don't know why.
Young's modulus.
Maybe it's just this one.
Okay. No, that's good. There was a heck of a lot of Young modulus questions in the database.
I did them. And so
You did them all?
No,
Okay.
Oh, wait. I did.
Well, let's start with simple harmonic motion, okay?
Okay.
Now, I think what I'll do, we haven't got a lot of time. So what I'm going to do is I'm going to give you a kind of tricky exam question I remember from many years ago on simple harmonic motion as kind of a homework. Actually, I can give you two. So I'll give you the first one. You can write it down. I don't remember what year it came from, but it's something like this. So you have a dock, okay, and do you understand? You can have what's called a low tide, and then later in the day you can have a high tide. Now I'm not 100% sure, but I'm pretty sure that the time it takes to go from low to high tide is 12 hours. Okay, so this will take 12 hours. Okay, and let me just... Right, and I need to give you some distances. We'll say this distance here, we'll say is 1 meter. and this distance here is 11 meters. We'll also say that currently it's now low tide, and we'll make the time noon. You know what time noon is, don't you? And that's now. And we have a boat. Now, I don't know if you've ever seen this, if you've been to the harbour, but when the tide is low, the boats actually sink into the sand. So this boat here is actually kind of stuck in the sand. And this boat needs the depth. No, how do you spell depth? As in D-E-B? D-E-B-T, isn't it? No.
That D-P-T.
That's what I had. That's what I had. Okay. Depth. Oh, my TH sounds. You Irish person. Okay, so it needs a depth of, let's say, 5 meters. So my question is, or the exam question was, at what time does the boat leave the dock? You know.
The dock.
Yeah, this is called the dock. Or harbour. Or whatever you want to call it.
Okay. So it's just 5 meters.
Yeah, so it's basically the question is, when will the tide be 5 meters high? Now you might be saying, Stephen, what has this got to do with simple harmonic motion? Can you spot it? Because, yeah, if you were to look at the motion of the tide, this is actually simple harmonic motion. It's, Gina, look up for a second. We usually think of simple harmonic motion being like this. But believe it or not, for the tide, it's simple harmonic motion, just extremely slowly. So it takes 12 hours to go whoop, and then 12 hours to go back down. Okay? Extremely slowly. I think it's 12 hours, or is it 6 hours now? Oh, it doesn't really matter. I'm starting to doubt myself. It doesn't matter. But if you Google later and discover it's 6 hours, fine, I'll believe you. But just use 12 hours for this one, okay? So this was in the exam as a section B question. And you can understand how a lot of students found it hard. Because it's not a normal simple harmonic motion question. But it's all the same formulas, you know. So I think this would be a good one to do for homework as practice for simple harmonic motion. And then I can give you another one the next day in class. Okay? When is our next class? Perfect. Perfect. All right.